Greetings, here is the how. Today, I will present the findings of our latest research on the prediction of coal flash characteristics and an evaluation of its recycling potential. It's crucial to understand why we rely on statistical data analysis methods for predicting the toxicity and the recycling potential of coal flash over direct measurements. As shown in the provided data, although the recycling rate of coal flash has surged over the past 2 decades, a concerning 40% of coal flash was still directed to landfills as of 2021. This ash is especially pertinent for reuse, especially as a low carbon infrastructure material due to its primary components, the calcium, aluminum, iron, and silicon are also key ingredients in cement and concrete. A major challenge in recycling coal ash arises due to the trace amount of heavy metals and toxic elements such as arsenic selenium. These elements don't just impede recycling but pose grave environmental and health risks, evidenced by incidents such as the leakage at TVA Kingston and Sudan Lake, where significantly high concentrations of dissolved arsenic and selenium were observed. Direct sampling and measurement for landfill coal ash aren't practical. The burning of coal as the primary energy resources can date back to the earlier 19th century, and landfill ash comprises ash from various years, making it challenging to date it precisely. Thus, we have turned to coal supply regions as functional predictors, differentiated by their geographical, geological, and economical attributes. Past studies from our lab have affirmed that coal supply regions play a decisive role in influencing the coal ash characteristics. Even when coal samples collected from different power plants with distinct combustion parameters, pronounced difference in elemental concentrations were noted based on the coal region origin. We also emphasize policy shifts, which can affect the power plant's coal sourcing decisions. The research objectives, to be elaborated in subsequent slides, commence with the creation of a comprehensive coal supply chain database. This database spans 50 years, encompasses geospatial data, provides detailed chemical data for coal flash, and integrates other pivotal information. Our intent is to harness this data to synthesize geospatial and chemical data for evaluating the recycling potential and to establish both linear and nonlinear regression model for predicting landfill elemental distribution. A secondary goal involves time series analysis of coal regions to discern if coal from identical regions consistently influence the coal ash quality. Preliminary observations suggest that such impacts can vary over time, necessitating judicious consideration in predict model. The last, but the most important target, is predicting coal flash characteristics and accessing its reuse potential by integrating historical data with our lab's analysis model. We use coal quantities from each region normalized as percentages serve as the predictor variables to predict the presence of major and amino elements, rare earth elements, and trace toxic elements in coal flash. The final slide shows the prediction outcomes from our involving model, emphasizing the major elements in coal flash and its spatial distribution across the US. These findings will be pivotal in evaluating the recycling potential of coal ash for construction applications.